Okay, good morning, all the students. Let's continue with our first lecture itself. Okay, in the previous session, one second, yeah. In the previous session, we started with lecture 1 under module 4, and we covered some concepts of fundamental probability. But as a continuation or to be strengthened on the basics, we'll just go through the concepts quickly once again before going to the next concept. Okay, so we have seen what is probability, what is inference, hypothesis, and prior probability. We understood that Bayesian reasoning provides a probabilistic approach to inference. So in order to draw some conclusions, rather than simply making a statement, or rather than making some hypothesis, formulating a hypothesis, or rather than simply making some conclusions, you are making that conclusion with some confidence, with some support, with some probability. Okay, that is called as Bayesian reasoning. So when I say this much percent of the Indians are literates, how do I make that statement? What is the support? I have studied across the population by taking some sample, and I have understood that this much of the Indian population are literates, right? So I'm trying to make that statement with some confidence. Say probability, the likelihood of that statement becoming true is called as the probability. Okay, so when I say I make this inference with 90% probability, means 90% proof I have in order to say that this much percent of the Indians are literates. Right? So when I'm making some statement, in order to make that statement with confidence, I depend on probability. I rely on probability, because probability will tell the chance of that statement becoming true in the circumstances given. Okay, so Bayesian reasoning provides the probabilistic approach to inference to draw some conclusions. And we also understood that probability is the chance of some occurrence of something. If an event has to occur, if an event occurs, that probability of that event is 1. If it doesn't occur, it is 0. Means it is true or false, reality or it doesn't occur at all, right? If an event, say when I roll a dice, in the probability of 1 occurring on the top or 2 occurring on the top, if 2 occurs, others doesn't come on the top, right? So that is called as probability in its entirety. It is either 1 or 0. Event occurs or doesn't occur. It is not that partial event occurs. You can't say that 1 or 2 occurs or 2 or 3 occurs on the top. Only one number will appear on the top when when a die is rolled, right? So the probability of a number appearing on the top is either 0 or 1. Okay, it is very straightforward. You don't have any half partial events occurring. So when I take a dice, there are total 6 chances, right? 6 numbers that can appear on the top. So the probability of 1 appearing on the top is 1 by 6. 2 appearing on the top is 1 by 6. 3 appearing on the top is 1 by 6. What do you understand by this? There are total 6 outcomes and the total probability is 1. A number appears or doesn't appear. So in order to make this 1, it is 1 by 6 plus 1 by 6 plus 1 by 6 plus 1 by 6. This happens for all 6 numbers. right? So that sums up to 6 by 6. That becomes the probability 1. So what is happening here? Each number is sharing the probability 1. That is why the probability of 1 appearing on the top is 1 by 6, 2 appearing on the top is 1 by 6, and so on. Right? So all these numbers have equal probability of appearing on the top when the die is rolled. So it is 1 by 6 plus 1 by 6 plus 1 by 6. Total, it counts to 1. It sums up to 1. Okay? So this is how you understand the probability. So if you want to tell this in the form of chance, you can just multiply it with 100. So what is the percentage of chance of a number appearing on the die? That can be calculated, okay? But that is not of our interest now. We are just focusing on probability. The probability can be calculated as the chance of a particular event happening, the likelihood of the event happening, whether yes or no, with what likelihood it may happen. Okay. So the likelihood of 1 appearing on the die is 1 by 6, 2 appearing on the die is 1 by 6, and so on. And inference is the conclusions we draw by observing some real world data. Okay, by observing some training examples. If we draw some conclusions, we call that as inference. Now, if you connect this inference with probability, then you are drawing that conclusions with some likelihood, with some support, with some confidence. Okay, and hypothesis is a statement you make. And prior probability is the data you have or knowledge you have about occurrence of something in that context. Say, as I gave you the example of number of patients recovering from the pandemic. Say, whenever some pandemic occurs in the history of mankind, then 70% of the people recover or 80% of the people recover. These are the facts that have been built by observing historical data. Okay, this is the prior probability of about the pandemic. Now, if I want to calculate what is the recovery rate with respect to COVID, then I can make use of this prior probability in calculating that. I'll show you how we use the prior probability in calculations of posterior probability or maximum a posteriori probability by using Bayes' theorem. Okay, and I have already given this introduction to you how Bayes' theorem or Bayesian reasoning provides the basis for learning algorithms that directly manipulate probabilities. Most of the algorithms we have seen so far doesn't use any probabilities. We have a hypothesis and we have that hypothesis to be consistent with the training examples. We always select, say, in finders algorithm or in candidate elimination algorithm or in ID3 algorithm or in backpropagation algorithm, wherever you take perceptron learning rule or delta rule. In all these algorithms, we are trying to find the hypothesis which fits the training examples in its entirety completely. It should be very consistent with the training examples. It should explain the behavior of the training examples. Only then we say that hypothesis is the most suitable hypothesis or the best solution for that given set of training examples. Okay, now in Bayesian reasoning, we have an added advantage. What is that advantage? We can say, we can select a hypothesis which is consistent with the training examples and find out its probability with how much strength we have that hypothesis. What is the likelihood of that hypothesis? Say you have 10 hypotheses. Among that, one hypothesis has 90% becoming true. 90% chance of becoming true. In that case, we say our probability for that particular, the likelihood of that particular hypothesis is very high. So we have some confidence in asserting that particular statement, in giving that particular statement as a conclusion, or selecting that hypothesis as our final hypothesis, right? We have also seen features of Bayes learning methods. and the practical difficulties in applying the Bayesian methods. Now let us see what is Bayes' theorem. Bayes' theorem is very important because this provides the basis for calculating the maximum a posteriori hypothesis. Maximum a posteriori hypothesis means, say if you have 3-4 suitable hypotheses, if you have 3-4 best hypotheses, that will explain that explains your training examples, or that are consistent with your training examples, then which one to select? Which has the maximum probability, which has the highest likelihood. That hypothesis will be your optimal solution, right? For that, you need to understand what is Bayes' theorem. In machine learning, we are often interested in determining the best hypothesis, right? Always we want the best hypothesis. In finders algorithm, in candidate elimination algorithm, what is our final objective? To find the best hypothesis which is consistent with the training examples. Remember, if a different set of training examples are given, your hypothesis may or may not be consistent, because you're only drawing a sample from the population. You're not studying the entire population. When I say Indian students are smart, I haven't studied entire Indian student population. I have taken a representative sample from the Indian student population, and I built my experiment on that particular sample, and I have derived some conclusions. I have derived some inferences out of my experiment, and that experiment is consistent with the sample I have selected, but it may or may not be suitable or best hypothesis for the other sample that we draw. That is why when we are drawing a sample, it should be representative. If it is representative, most of the times your hypothesis that you have built on your sample will also apply to the larger population. This is called as generalization capability of the hypothesis. Okay, so whenever you're building a hypothesis, whenever you're making a statement about a population, you have to make that first by first building it on representative sample. Remember, the sample should be representative. If the sample contains all sorts of people from the population, then the hypothesis you built on that particular sample will be generalized, can be generalized to the larger population. Okay, that is what is called as generalization capability of the machine learning model. Whenever you are taking some algorithm, building a machine learning model by taking some set of training examples, that model should be generalizable. Means when new data is given, it should be able to predict well with the new data also. Did you understand clearly? So whenever you are taking a sample, that should be a representative sample. Remember that. Now in machine learning, we are often interested in determining the best hypothesis. Best hypothesis means which is consistent with the training examples, which explains the behavior of the training examples from some space H. That hypothesis might have been taken from the hypothesis space H, given the observed training data D. Did you observe here? H taken from the hypothesis space capital H, given the observed training data D. Always we highlight this point. Given the observed training data D means this is the best hypothesis for this training examples given. Taken a different training examples, this may be the best hypothesis or may not be the best hypothesis. But your objective should be to build the hypothesis which can generalize to any set of training examples, which can generalize well to any set of training examples. Okay? Now, one way to specify what we mean by the best hypothesis is to say that we demand the most probable hypothesis. Most probable hypothesis means the likelihood of that hypothesis becoming true given the data D should be very high. It should be as much as 95%, 97%. In that case, we say that is the most probable hypothesis. It has most probability of becoming true. with the given training examples. Okay, that match is perfect. One way to specify what we mean by the best hypothesis is to say that we demand the most probable hypothesis. That is why I'm repeating this again and again. We demand the most probable hypothesis. Again, this tail is associated. Did you observe? Given the data D, we are not committing, we are not guaranteeing that this hypothesis is true for any type of training example. We are just promising up to some extent, that is, given the training examples D, this is the most probable hypothesis, plus any initial knowledge about the prior probabilities of the various hypotheses in H. Always it is better also to have prior probabilities of other hypotheses in the hypothesis space, which will actually improve the probability estimation of our most probable hypothesis. So if you don't have prior knowledge about the hypothesis, then the likelihood calculation is somewhat worse. But if you have prior probability details, then your probability calculation is much accurate. Got it? I'll show you how it can be done with an example. Bayes' theorem provides a way to calculate the probability of a hypothesis based on its prior probability. We calculate by taking the prior probability, any underlying expert knowledge, whether we can use that in calculating the posterior probability. Okay, that is why when we are taking the prior probability, it is always better to take it from the domain experts, so that we'll get a better measure about this prior probability, which would assist in helping us to which would assist in calculating the posterior probability. The Bayes theorem provides a way to calculate the probabilities of observing various data given the hypothesis. For the given hypothesis, what is the probability of observing various data? That also can be calculated, and the observed data itself. We have also seen what are these notations: P of H, P of D given H, and P of H given D. P of H is the initial probability that hypothesis H holds before we have observed the training data. Training data is not yet given, but we have the probability of that statement. That is called as prior probability. Say I say that 90% of the people in the world recover from pandemic. When I say that, that is the prior probability. Still, no data is given about the COVID patients, but only data about overall pandemic in the previous years is available. Okay, and that is derived by expert knowledge. Maybe people in the healthcare or scientists in the healthcare domain, they have made this particular statement or created this fact that 90% of the world population can recover from a pandemic as monitored in the previous pandemic cases. Okay, so that is called as prior probability. P of H is called as the initial probability that hypothesis H holds becoming true before we have observed the training data. Still training data is not available. That is called as the prior probability. If we have no such prior knowledge, then we might simply assign the same prior probability to each candidate hypothesis. Say the expert knowledge and expert suggestions are not available. Expert knowledge or subject matter expert are not available for us. In that case, say if you have 5 hypotheses in the hypothesis space, then all those 5 will share the probability equally. Means it becomes 1 by 5, 1 by 5, 1 by 5, 1 by 5, and 1 by 5. So that it sums up to 1. The entire hypothesis space probability is 1. Okay. Now what is P of D? The prior probability that training data D will be observed. In this case, no hypothesis is given, but the probability of the training data being observed. is given. That is called as P of D. Now, what is P of D given H? The probability of observing data D given some world in which hypothesis H holds. Okay, this will be made more clear with the example. The probability of observing data D given in some world hypothesis H holds. Okay, so what is the probability of observing these symptoms given some statement is made about the patients? Okay, that is PD, probability of D given H. Now, what is probability of H given D? The probability that H holds given the observed training data D means the consistency of your hypothesis with the training examples D. That is called as the posterior probability of H. This is very important. This is what we are going to calculate. What is the probability of hypothesis H becoming true given the set of training examples? What is the probability of H being consistent with the training examples given, that is D? That you have to calculate. That will give you what is the most probable hypothesis in your hypothesis space, and that is your final conclusion that you make. That is the inference that you draw from the experiment with some likelihood. That likelihood is the probability that is calculated, and that is posterior probability, and that is represented by P of H given D. P of a probability of observing the hypothesis in consistency with the training examples D. Okay. Now, what is Bayes' theorem? It provides a way to calculate the posterior probability. Remember, this is the posterior probability of H given D. Do not get confused. It is not D given H. You are trying to calculate the likelihood of a hypothesis to become the most probable hypothesis, to become the best suitable hypothesis. Okay, that is why H comes first. You're calculating the probability of a hypothesis in consistency with the given training examples D. That is your goal. That is what you are calculating. And that can be calculated by using Bayes' theorem. It provides the way to calculate the posterior probability P of H given D from, what is the formula? From the prior probability P of H together with P of D and P of D given H. So this is the formula you have to remember. P of H given D, the posterior probability of hypothesis given the training examples, is calculated as the product of probability of D given H multiplied by probability or the prior probability of H divided by the probability of D. Okay? Did you understand? Probability of H given D is equal to probability of D given H. You know what is D given H? Probability of observing the training examples in a world where the hypothesis is, where this hypothesis is true. Okay, that is P of D given H multiplied by the prior probability of hypothesis. Means there is a fact, but still training examples are not there to prove that fact. That is called as prior probability P of H divided by prior probability of D. Means you don't have hypothesis, you just have the training examples. Independent of the hypothesis, you have to build the hypothesis. That is prior probability of D. You have the training examples, observed training examples, but still hypothesis is not available to you. That is called prior probability of D. Okay, so P of the posterior probability of H given D can be calculated from P of D given H multiplied by P of H divided by P of D. Okay. Now, what is maximum a posteriori hypothesis? You have lots of solutions. Now, which solution is having good chance of becoming a good chance of being consistent with the training examples. Say you have hypothesis 1, hypothesis 2, hypothesis 3 in your hypothesis space H. Now, which is having the maximum likelihood to suit the training examples? That is called as maximum a posteriori hypothesis. Say this has 0.2 probability, this has 0.3 probability, but this hypothesis has 0.5 probability for holding good with your training examples given. Then this will be your maximum a posteriori hypothesis. Why we are telling a posteriori hypothesis? Not only the likelihood of the hypothesis, but the likelihood of that hypothesis in consistence with the training examples given. That is important for us. We don't want simply P of H. We want P of H given D. That is important. The fact is not important. Whether the fact applies to that given training examples, that is important. That is called as probability of H given the training examples. This fact becoming true for the given training examples, that is called as posterior probability. And the hypothesis is called as maximum a posteriori hypothesis, or simply we can call it as MAP hypothesis. Hereafter, when I say MAP hypothesis, you should immediately, it should strike in your mind, I'm talking about maximum a posteriori hypothesis. Okay, so I'm trying to find out the hypothesis that has the maximum likelihood of becoming true with the given training examples. That is my MAP hypothesis. Got it? In many learning scenarios, the learner considers some set of candidate hypothesis H, yes, and is interested in finding the most probable hypothesis H belongs to H. Again, given the data, observed data D. Okay, so you're not only interested in P of H, you are interested in P of H given D. This hypothesis, whether it is in consistency with the training examples given, that is D. Did you understand, students, now what is MAP? You have lots of hypotheses. You have the training examples given. Now, which hypothesis is having maximum likelihood so that it better explains the training example set D? That is your maximum a posteriori hypothesis, or that is called your MAP hypothesis. Now, any such maximally probable hypothesis is called a maximum a posteriori hypothesis, right? Did you understand clearly? Ask me if you have a doubt. Students, did you understand what is maximum a posteriori hypothesis?
Yes, ma'am.
Yes. Any other students? You have a doubt, ask me now, because all the later concepts are based on this idea. If you don't understand this theoretical concept, you can't understand what we are going to deal with further. Okay, so I'm proceeding, assuming that all of you understood. Now we can determine the MAP hypothesis by using Bayes' theorem to calculate the posterior probability of each candidate hypothesis. Okay, now we have some set of hypotheses in hypothesis space, but we don't know what is their posterior probability. Now, how do you calculate that? The maximum a posteriori hypothesis is nothing but the argmax of P of H of D. What is this? P of H given D is called your posterior probability. Now, you are interested in the maximum hypothesis, maximum likelihood of the hypothesis. You calculate this posterior probability for P of H1 given D, P of H2 given D, and P of H3 given D, right? But do you prefer all the hypotheses? You find out the hypothesis that is having the maximum probability. of being true with the given training examples, right? That is why we are using this argmax. You are interested only in the maximum likelihood hypothesis, the hypothesis that is having the highest probability. That is your most probable hypothesis. That is why you are using argmax for all hypotheses that belongs to H. That is what we have given here. H belongs to H. What maximum you want to find out of the posterior probability. Of all the posterior probabilities, you want the maximum posterior probability, and that gives you the maximum a posteriori hypothesis, which is the most probable hypothesis for the given training examples D. Got it? Now substitute from your Bayes theorem. You have P of H given D as P of D given H multiplied by P of H divided by P of D. You just substituted the Bayes theorem equation here. For the posterior probability P of H given D, you are substituting right hand side of the Bayes theorem. Did you understand? Then you can simply neglect the denominator P of D. Why? Can you tell me why, students? You are omitting this term, probability of observing the probability of the observed training examples, because that is not related to the hypothesis still. It is just the prior probability of the observed training examples. You still have no effect of H on this D. That is why you are omitting that from the denominator. And finally, you have argmax P of D given H multiplied by P of H. Now, in some cases, we'll assume that every hypothesis in H is equally probable a priori. A priori means beforehand, when you don't have knowledge about the prior probabilities. In that case, you assign equal probability to all the hypotheses in the hypothesis space. Say I have 3 hypotheses in my hypothesis space H. In that case, I assign 1 by 3, 1 by 3 and 1 by 3 to all the hypotheses until I get some knowledge about the posterior probability. Okay, so if I have domain knowledge, I can give some prior probability. But if I don't have domain knowledge, then I can assign equal probability to start right away. Got it? That is what is represented here. Now we can further simplify the above equation as, now we also understood that P of H is a constant when you don't have idea about the prior probability. It is constant throughout. Say if I have 3 hypotheses, I said my probability assigned is 1 by 3, 1 by 3 and 1 by 3. Is it varying? No, it is a constant. So I'm not interested in the constant. I'm just interested only in the hypothesis which is having effect on the training examples. That is why I am removing this term also. So my final maximum likelihood hypothesis is argmax H belongs to H, P of D given H. It has become simple thing now. What we understood? The maximum likelihood hypothesis is nothing but the probability of observing the training examples D given the hypothesis, given a statement that we have made. Okay. So that is your maximum likelihood hypothesis. In this, P of D given H is often called the likelihood of the data D given the hypothesis H, and any hypothesis that maximizes P of D given H is called the maximum likelihood hypothesis. That is represented by HML. Did you understand how H map has been transformed into HML? Both are same, but we are just omitting all the constant values and finally deriving this term. Okay. Now let us see very interesting example. Consider a medical diagnosis problem in which there are 2 alternative hypotheses. Okay, what are those two alternative hypotheses? That the patient has a particular form of cancer, that is one hypothesis, and the patient does not have cancer, that is another hypothesis. Okay, now the available data is from a particular laboratory test with two possible outcomes. Now we have the available data as data with two possible outcomes. As positive means the patient having cancer, and negative the patient not having cancer. Okay, so this can be represented as a probability, right? Patient having cancer, probability is 1. Patient doesn't have cancer, probability is 0, like that. Likelihood of positive and negative. I'm just explaining regardless of any other data. Now let us proceed forward and see how Bayes' theorem can be useful in calculating the posterior probability of a hypothesis. The available data is from a particular laboratory test with two possible outcomes. Plus means the patient is diagnosed with cancer, and minus means the patient is not diagnosed with cancer. Okay, we have prior knowledge means prior probability. We have prior probability that over the entire population of people, only 0.008 have this disease. This is a fact that has been built through some experiment. Okay, it indicates that 8 out of 1000 population, 8 out of 1000 over the entire population have this disease. Okay, we generally say that, right? Say if you take 1 out of 5 students are having high IQ in India, or 5 out of 10 students are having high IQ in India, means that is a fact that have been built, that is a hypothesis that have been made by doing some other experiment. This is the prior knowledge being given, which can serve us in our current context to calculate the posterior probability. So what is the prior probability that is given here? 8 out of 1000 population, out of the entire population, 8 out of 1000 people have this disease. Okay, that is a statement that is made. That is called as the prior probability, prior knowledge about that particular disease. Okay, now furthermore, the lab test is only an imperfect indicator of the disease. Lab test is not 100% true, may not be 100% true. It is an imperfect indicator of the disease. Okay, now how do you say that a patient diagnosed as positive, whether he is really having cancer or not? Understand the problem carefully. A patient is diagnosed, I'm saying diagnosed. I'm not saying whether he is really having cancer or not still. The patient is diagnosed as positive. Now, does he really have cancer or not? That is our problem. So that is why here they are just giving us, they are giving an indication that the lab test is only an imperfect indicator of the disease. Means if a patient is diagnosed as positive, we can't completely rely on that report that he has cancer. Okay, it is an imperfect indicator of the disease. So what do you do next? How do you say that the patient has cancer or not from the lab test that is given? That is your problem. Now, some more data is given. What is the data? The test returns a correct positive result in only 98% of the cases in which the disease is actually present. Means when the patient is having cancer, he is also diagnosed to be having cancer 98% of the time. 98% of the time the reports are correct. 2% of the time it may be wrong. But this is derived from the studying the historical data again. Okay, now what is the second statement? The test returns a correct negative result in only 97% of the cases in which the disease is not present. Means when the patient is not having cancer, He is also diagnosed as not having cancer in the lab. He got a negative result, but only 97% of the time. 3% of the time, though the patient is not having cancer, he might be diagnosed as having cancer. 3% of the time, right? Now, in other cases, the test returns the opposite result. That is what I said. 2% of the cases, it returns a positive result. And 3% of the cases, it gives a negative result, opposite. When they don't have, they're diagnosed to be having cancer. When they have cancer, they're diagnosed to be not having cancer. Okay, that happens 2% and 3% of the time respectively. Now, the above situation can be summarized by the following probabilities. Let us calculate the probabilities first from the available data, from the given data. Now, what is the probability of having cancer? Probability of a person having cancer, that is called as the prior probability. That prior probability is given as 8 for 1000 population, right? 8 out of 1000 people have cancer. In that case, what is the probability of cancer occurring in the population? It is 8 by 1000, that is 0.008. This is 8 by 1000, or 8 out of 1000 people have cancer. That is the prior probability, and that is represented as 0.008. Now, when 8 out of 1000 people have cancer, 992 people doesn't have cancer, right? So that is 992 by 1000. These many people doesn't have cancer. So what is the probability of not having cancer in the population? It is 992 by 1000, that is 0.992. Did you understand this? These are the prior probabilities of having cancer and not having cancer. This is very clear for you now. Now, come to the next step. What is the probability of a person being diagnosed with cancer, means diagnosed as positive, when he has cancer? That is correct test only. And they told us that 98% of the time the diagnosis is correct. That is why it is 98 by 100. So it is 0.98. Now, 98% of the time, it is giving correct diagnosis when the patient is having cancer. But 2% of the time, it is giving wrong result. Means when the patient is having cancer, when the patient is not, when the patient is having cancer, it is diagnosing as not having cancer, negative. That is happening 2% of the time. 98% is given means automatically we can calculate the other side. When the patient is having cancer, he is diagnosed as positive 98% of the time. True, that is correct diagnosis. Now, when it is wrong diagnosis, 2% of the time it is wrong diagnosis. Means whenever a patient is having cancer, he is still diagnosed as negative. That is 2% of the time. That is given as 0.02. You can't represent probability in terms of percentage. That is why you're converting it into a value between 0 and 1. And that probability is 0.02. Okay, now next one. What is the probability of, come to this term, what is the probability of a patient being diagnosed as negative when he is not having cancer? That diagnosis is also correct for 97% of the time. For 97%, it is giving correct result. Now, for 3%, it is giving wrong result. Means, whenever the patient doesn't have cancer, still he is being diagnosed as having cancer, positive. That is 3%. So, it is represented as 0.03. Suppose, now we have all the probabilities, very well calculated. From the data given, we have also calculated the opposite of that. That is, when what is the probability of a patient having cancer, but he is not diagnosed to be having cancer. That also we calculated. Now all these calculations are very clear for you. Now the actual question arises. Suppose we now observe a new patient for whom the lab test returns a positive result. Should we diagnose the patient as having cancer or not? How should we diagnose him? We can't rely on the lab result. That because he is diagnosed as positive, he is having cancer. We can't say. Well, we can't say with confidence. Let us associate probabilities to it. Let us associate likelihood to it. What is the likelihood of that patient really having cancer when he is diagnosed as positive? How can we do that? By simply applying the formula. Very easy it is. What is the maximum a posteriori hypothesis? H map means what is the probability of that patient having cancer when he is having cancer, when he is not having cancer. Let us calculate both of them and see which probability is more. Okay, so how do you calculate that? Probability of D given H, that is probability of a patient being diagnosed as positive when he is having cancer, multiplied by probability of general population having cancer. What is the probability of a person being diagnosed as positive when he is having cancer? 0.98. And what is the prior probability of cancer? 8 out of 1000 population. So it is 0.008. So the probability is 0.0078. Now, next. You should calculate both, right? The patient being diagnosed as positive and he is having cancer, and the patient being diagnosed as positive and not having cancer. Okay, so next one is the patient diagnosed as positive but he is actually not having cancer, multiplied by the prior probability of not having cancer. That is your formula, right? That is what you are calculating. So the patient being diagnosed positive when he is not having cancer, wrong diagnosis, 3% of the time. That is 0.03. And what is the prior probability of not having cancer in the larger population? 992 out of 1000 people doesn't have cancer. So it is 0.992. What is the final probability that is calculated? 0.0298. Now students, tell me what is your inference? Whether the patient have cancer or doesn't have cancer. The lab result is he is diagnosed as positive. But after you calculated your maximum a posteriori hypothesis, whether he is having cancer or not, where is the probability higher here? This case or this case? Speak out, students. It's time for your next class. What do you infer from this calculation? This probability is the patient diagnosed as positive when he is having cancer. This calculation is the patient diagnosed as positive when he is not having cancer. Which probability is high? Which probability is high, Tanuj? Anusha? Surya? Are you there? Tejashwini? Can't you see which probability is high here?
Yes, ma'am. Lab
Yes?
test, ma'am.
Lab.
Second one or first one?
Second one, ma'am.
Second one is having higher probability.
Second one, ma'am.
So what do you infer?
Yes, ma'am.
What do you infer? What do you conclude? Whether the patient has cancer or doesn't have cancer?
Doesn't have cancer.
Very good. He doesn't have cancer
Doesn't have
because
cancer.
this is the probability. I'm repeating again. This is the probability that the patient is diagnosed as positive when he's having cancer. This is the probability that the patient is diagnosed as positive when he is not having cancer. This probability is high. What is your maximum a posteriori probability? The patient is diagnosed as positive when he is not actually having cancer. So you can infer that the patient doesn't have cancer. Did you understand clearly? Important calculation. So in your next class, we'll see what is Bayes' theorem and how it is associated with concept learning. Now, can you quickly answer these questions before you join your next class? What is P of D given H? When you are understanding the concept, don't simply read it as P of D given H. Read it as probability of observing the training examples given a hypothesis H is true. Means you have the data about H. Now, what is the probability of observing the training examples in compliance, in consistency with this hypothesis? Whether this training data is suiting with this hypothesis that has been made. That is called as probability of D given H. Probability of observing the training examples D given a hypothesis is true. That is how you have to read this. Okay? Do not get confused between H given D and D given H. If you read when you are understanding the concept, it will be very clear for you. Read it. Do not simply say D given H. Probability of observing the training examples D given hypothesis H is true. Now, what is the next one? In the same way, can you repeat the second term? Students? Ajay? Yes.
Probability of phase H with given training example D.
Probability of hypothesis,
Okay.
right?
Hypothesis.
Probability of hypothesis H given the training examples D. Correct. Probability of hypothesis being true in consistency with training examples D. In that way also you can say. Good, Umehani. Then example for prior probability. Any example can you give?
Mortgage case, ma'am.
How do you give a statement there?
It is the default by 2%.
Default?
Default, ma'am.
Okay. Yeah, it may be considered like that.
And home mortgage, ma'am.
Okay. Okay, so when you're trying to say this, right, say 100 people have taken the loan. Out of that, 90 people, most of the time, 90 people pay back the loan. In that case, we can say that 90%, 90% of the customers pay the loan back. It is 0.09. 0.9. It is 90 by 100, right? So it is 0.9. Probability is 0.9. Prior probability that customers pay back the loan is 0.9. Means 90% of the time customers will pay back the loan if that bank is giving the loan. That can be taken as a prior probability. Example for posterior probability.
For instance, there are 50% girls in a class and 50% boys in a class. Like 50-50 chances.
No, we are not saying about the gender, right? The features among them. We are not categorizing what is the problem at hand is not categorizing them with respect to their gender. We are trying to say that how many of the students perform well. In that case, we are not bothered about the gender. We say 80% of the students. Again, if you want to say only boys' performance in the class, then you take 50% of the boys as your 100% population. Then you're not bothered about girls. Or you take 50% of the girl population as your 100% sample. Did you understand what I'm talking about? Say your
Yes, ma'am.
class has 100 students. Now in that you have 50 girls and 50 boys. Now, when we are studying about the overall performance of the students, I can say 95% of the students are performing well. But my question is, how many of the girls are performing well? In that case, I take only girls sample. In that case, this girls 50 will become my 100% population. Now, among them, say 40 are performing well. So 40 by 50 into 100. That means 80% of the girl students are performing well. Means 0.8 likelihood of girls performing well. Did you understand?
Yes, ma'am.
Okay. So posterior probability is, say, a transaction being categorized as fraudulent when it is really fraudulent, or the property of a transaction being categorized as fraudulent when it is not actually fraudulent. That can be treated as posterior probability, means observing the hypothesis in consistency with the training example that is given. When a new data point is given, a new transaction is given, a new patient data is given. Now we are trying to find out what is the probability of it being genuine or not being genuine with respect to the new data point. That is called as posterior probability. Okay? Are the concepts clear, students? Okay, you can join for your next class. Bye.